I was saying, we're very happy to have Juan Maldacena from IAS, and he's going to tell us about comments on the double-sided double cone wormhole. Over to you, Juan.
Okay, thanks for the invitation. It's a pleasure to be there virtually. And so this talk is based on some work that already appeared in the archive, and it was done with Yimin Chen and Victor Aibo. So in Einstein's theory of gravity, the geometry of space-time is curved and dynamical, and it is also natural to consider other topologies for space-time. So in the quantum version of the theory, we think we should sum over all these geometries and topologies. And a simple space-time geometry is that of a wormhole, so it connects two separate asymptotic regions, as you probably have heard. Now, such wormholes have long raised some puzzles, and a proposed resolution involving averages of coupling constants was discussed in the 80s. Now, recently there have been two very interesting applications of this type of wormholes. One was for calculating the page curve and the entropy of Hawking radiation. And the second one is calculating the ramp in the spectral form factor. So this talk will be about this second type of wormhole. It will be about studying some aspects of this wormhole. So I will first review what Saad, Shenker, and Stanford did, and then we'll discuss which issues we are addressing. So we'll discuss some gravitational aspects of that double cone wormhole that explains that ramp in the spectral form factor. Now, what is that geometry? So that geometry is defined for any Schwarzschild black hole. Let's say, for example, let's say an ADS Schwarzschild black hole. I think it should also be defined for a rotating black hole, but we didn't analyze that case in detail. So we start with the Penrose diagram, or the full space-time geometry of the two-sided black hole. And then we quotient by a boost isometry. So there is here an isometry of this geometry, which is just the usual Schwarzschild time translations, which moves you up in time in the right side and down in time in the left side. And we then quotient by the action of that isometry by a finite amount. So we identify the Schwarzschild time t with t plus capital T. And so we get a geometry which contains a circle in the time direction. Now that might seem confusing, but it will be related to the type of observable we are computing. It's a somewhat funny observable. We'll discuss it in a second. But for now, we are discussing just the space-time geometry contains this circle, and that circle shrinks at where the horizon was before, and we have a similar geometry on the other side. So that's the geometry we'll be talking about. There is some kind of singularity here at the center. We'll have to deal with it, and that will explain in the next few slides. So we'll see that we will need to make a small complex deformation that we'll discuss in more detail. Now, why are we interested in this geometry? So Saad, Shenker, and Stanford proposed that this is a geometry that contributes to the spectral form factor, in particular to the connected part of the spectral form factor. So what is the spectral form factor? Well, you start with the partition function of the theory, trace e to the minus beta h, and then you give some imaginary part to the inverse temperature. So T here is some time. It should not be confused with the temperature. I now realize that there might be a confusion with the temperature. So we'll always have beta, and capital T is some Lorentzian time direction. So we consider this particular analytic continuation of the partition function, and then we take this trace. So we see that if beta is equal to 0, then this would be like the trace of the evolution operator. Now that's not an observable which is particularly easy to measure. Well, it could be measured. I mean, this object is equivalent to taking the thermophile double state and then doing this Lorentzian evolution and then overlapping it with another thermophile double state. So that would be one way of computing this quantity. in an experiment. So it will involve producing the thermophile double state. But we see that on each side we get this particular trace, and that's the somehow origin of this Euclidean time direction. Is due to the particular observable that we are computing. Now the idea is that we compute this, and then we take its complex conjugate and we multiply them. And if we express this in terms of a sum of energy eigenstates, we have a bunch of oscillatory phases, and then these phases at t equal to 0, they are not phases, they are numbers, they add up. But when t becomes non-zero, they start canceling, and we start getting something smaller. And then eventually, at extremely long times, basically we get some noisy signal around something called the plateau value, some constant average value. And before that, we have some region where we have this structure where in average, so we average over many realizations, or we average over the value of this time, we get some straight line. Now, this particular plot here was produced by using the SYK model, so a particular quantum mechanical theory with finite n. So for each particular realization, you get the red curve with many oscillatory features. If you in this case, they averaged over couplings, and then after averaging over many samples, you get the black curve here that has the more clear ramp. So this is something which is linear in the time direction. So we'll be focusing on this region. Perhaps we will explain where this comes from, and from the point of view of the quantum mechanical system, and then what the gravity solution is. Now, this average ramp is thought to arise from the distribution of energy eigenvalues. So the idea is that for a chaotic Hamiltonian, the energy spectrum is expected to have random matrix statistics. So the distribution of energy levels is the same as the distribution of the eigenvalues of a random matrix. In particular, for energies that are close but not too close. So not too close means energies further than the typical spacing between two nearby energies, but less than the whole width of the distribution. Then we expect that the correlation function between two energies, or the density-density correlation function of energy eigenvalues, should have this very universal form with a universal coefficient. I will explain a little more where this comes from in the next few slides. But for the moment, let's assume that's the case, and let's just see where the ramp comes from. So the idea is that we define this, we define this quantity e to the minus I ht, and then we'll put here a window function, which is some function that is localized around some energy. So some energy, let's say, somewhere in the spectrum. So that it could be a Gaussian, for example. And then we are going to take this quantity and then take the square of it, and then average over maybe microscopic couplings, or average over this time t. So when we do that, so we get, we are computing this average. So then we will have an integral over two energies, E and E prime. And there will be two of these window functions, one evaluated at E, one evaluated at E prime. We're going to approximate that as being the same energy E. And then we'll have also an energy over the difference of energies. And that will be multiplied by this phase. So one factor e to the ite comes from one of the factors in C, and the other one comes from the other factor. And there is a disconnected piece where we average, where there is no connection between E and E prime. And then there is this connected piece where we have some correlation between the energies. And if we have a formula of this type, then we get that we have to do the Fourier transform of this expression. And the Fourier transform of this 1 over e minus e prime squared is just simply a linear function in T. So just you can see that by dimensional analysis, and you can also see it more precisely. So it's the absolute value of T.
I have a question.
Yes, please.
So, I mean, you have this delta function and then you have 1 by e minus e prime whole square. This seems to diverge.
Yes, this diverges at low at when e is equal to e prime, but that divergence is somehow absorbed in the disconnected piece. So in the piece that has a separate average over e and e prime.
No, what I mean is if you have the delta function, doesn't it set e equals e prime in the integral?
I don't think I talked about any delta function here. Which delta function?
Oh, I see. Okay, fine. Sorry.
So this is not a delta function. This is just the integral over e minus e prime.
Okay, sorry.
Was that the question?
Yeah. Sorry.
Okay. Yeah. Yeah, and also if so here we're considering e minus e prime, which is relatively large. So we are focusing on the piece that is linear. There is also when e minus e prime becomes very small, so comparable to the spacing between energies, this distribution changes, and that will translate here into a change of this expression when T is very large. So when T is sort of the inverse of the energy spacing, then this expression changes. We go from the ramp to the plateau, to what we call the plateau. But throughout these talks, we'll be concerned only with the ramp. So the logic I was trying to explain is how we go from, well, I was trying to explain the relationship between the ramp and this distribution of energies. So the fact that we have this energy distribution and that the coefficient is related to the fact that the coefficient here is universal. Now, the double cone wormhole is supposed to be computing this correlation of energy levels. So that's supposed to be computing exactly this thing here. And the idea here is that the piece that is linear in T comes from a particular zero mode where we have this geometry, and then we can rotate the left side of the geometry relative to the right side of the geometry. And because the total volume here is T, that's where we get the factor of T. So that's the idea. Now, this wormhole is very universal, so it does not depend on the details of the gravity theory. So it's true in, let's say, JT gravity, in 3D gravity, 4D gravity, 10D gravity, etc.
Sorry, Juan, can I just, sorry to interrupt, but can I just ask for a clarification?
Yes.
The double cone is supposed to be thought of as the beta equal to 0 limit then of that spectral form factor. You just have the imaginary T parts, is that correct? Or
Yes. So it will be viewed as the version where we have some function f. You will see where this function f will appear in a second. For now, I'm slightly vague. We'll be a little more precise later.
Okay, thank you.
Yeah. So the point that I'm trying to explain right now is that there is some connection between the ramp and this energy distribution. Well, we'll see in more detail the relation to this geometry later. Okay. Now something. So this is one of the points of this talk, and our paper was to understand the normalization of this double cone contribution to see whether for any theory of gravity we get the right normalization as we expect from the random matrix theory. So first, let me try to explain where this number comes from in random matrix theory. And notice I would like to emphasize again that this is independent of the system size. So whether the matrix is an n by n matrix with any n, you get this distribution. And but this is of course assuming that all the eigenvalues of these matrices or the Hamiltonian is completely chaotic. Okay, so it's completely randomized. So if the Hamiltonian has various sectors, for example, a conserved charge, then for each value of the conserved charge, we'll have this distribution. And if we sum over all the conserved charge sectors, then we'll get this, and we'll get a factor proportional to the number of conserved charge sectors. So for example, if we have a C2 charge, then we'll get an extra factor of 2 in this expression. Okay, so let's try to understand where this number comes from. So it comes from random matrix theory. And so you're familiar that in a random matrix, we have some van der Monde determinant, and that leads to, if you think in terms of the density of eigenvalues, then in the action for the density of eigenvalues, you'll get the term that is proportional to log of lambda minus lambda prime, where lambda is the eigenvalue. So here, lambda will be E, the energy of the system. And so this quantity involves computing the correlation between two energy densities. So it involves computing the inverse of this kernel, and the inverse of this kernel is precisely this E minus E prime. Okay, so that's where it comes from. And the fact that that we have a particular coefficient here is related to the fact that when we look at the van der Monde determinant, there is some particular coefficient here in front. Okay? And this is the coefficient for the GUE, so the general unitary ensemble. So where we have Hermitian matrices, we're assuming a Hamiltonian with no extra symmetries. One could consider the case with extra symmetries, but we'll not discuss that here. So the question is whether we can reproduce this normalization from gravity. So this was reproduced in JT gravity by the Saad, Shenker and Stanford paper. And now we just would like to do it in general, understand a little bit better what fixes it. So that's, as we explained before, that's the same as determining the coefficient of the ramp. Yes?
How robust is this factor how robust is the dependence on the randomness, the measure that one uses to do the random matrix integral?
Well, it does depend on the measure in the sense that, well, when we have a random matrix, if we have a measure that is, let's say, a single trace function of the matrix, or in general is somewhat independent of the matrix, of the measure, except if you pick very weird measures. Okay, so the idea is that the eigenvalue distribution for a random so this result of this, the simplest version of this result is if you just take the ordinary measure for a random matrix, which could be, let's say, a single trace function of the Hamiltonian.
And them to believe or expect such a measure for quantum field theories at high energy?
Yes. So we expect that for somewhat nearby energies, it's likely that we'll get some random matrix expressions. As we will see later, from gravity, we will not get exactly this. We will get some deviations. So we expect this only when the system becomes fully chaotic. So there is a general conjecture that for chaotic systems, the energy distribution should approach that of the random matrix. So that is, as far as I know, a conjecture for general quantum systems, and is perhaps even more of a conjecture for quantum field theory, if that's what I'm asking. I don't think this has been proven in any way.
Excuse me.
Thank you.
Excuse
Yes.
me. May I ask a question?
Yeah.
Hi, Juan. That's Volodya. Usually in unitary matrix ensemble, you have the universal distribution for closed eigenvalues, which contains sine E minus E prime times rho over E minus E prime. Where does sine go in this situation?
Yes. So this is indeed that sign, but expanded for very large values of the argument. So if you take that distribution that contains a sign and you expand it for large values of the argument of the sign, then there is you take the average. So there is some oscillatory piece. So it's really a sine squared. So if you average the sine squared to be, let's say, 1/2, there is a denominator, which is this expression 1 over E minus E prime. And that's what we are discussing here.
It's sort
So
of
we're not, yeah, so that the precise, so the particular sign form and so on is relevant for the transition between the plateau, the ramp and the plateau. And we're not going to discuss that. So we are here looking at this eigenvalue distribution for relatively large large compared to the typical eigenvalue spacing, to the minimal eigenvalue spacing.
Thank you.
It's only a part of that expression.
So,
I
Juan,
have a
could you be
question.
more, excuse me, a little
Yes.
more precise about large compared to this? So, the typical spacing between energy eigenvalues, I suppose, of order e to the minus s. Here, I suppose you're considering much larger spacings, presumably which has 1 over s or 1 over s to some power. Is that correct? Or is it much smaller than that?
Yeah, so for this discussion to be valid, it has to be much larger than e to the minus s, and much smaller than some number of order 1 over s, which is the fluctuations of the energy.
Right. But we don't want to, are we allowed to consider e to the minus s by 2, for instance, or that's too small? That's too small, right?
I think from what, well, no, a factor of 2 would not be now. Yes, that would be fine. Yes.
I have a question.
Yes.
So, I mean, when you are saying that e minus e prime is always large, and you're using that in the integral, there would be situations where it becomes small, and then you have to use a sign, right?
Yes.
So,
That
I mean,
corresponds to the region where t is very large. So if we're interested in the, so when we had that integral, let me see, what's the integral? When we have this integral, you can see from the form of the integral, what for a particular value of t, there will be some particular value of the energy difference that will make most of the contribution. And as long as this t is not exponentially large in the entropy of the system, the typical e minus e prime that contributes will be relatively large compared to the typical energy spacing.
okay.
So that translates into a range of these. So when we're looking at this, we're not interested in a time which is very large. We just focus now on this region. I mean, of course, it's interesting to ask about this region, and that's more complicated. That's not what we are going to be discussing here. We're only going to be discussing this region.
Yes.
Presumably, there will be another type of wormhole that contributes in this region.
Okay.
Sorry, really stupid question. Why? How did inverting that log give you 1 over e minus e prime square?
Yes, so that was the inverse, right? So you have some kernel, so it's a function of 2 e minus e. So let me say it the following way. So if you have e minus e prime, let's say this is lambda minus lambda prime, and then you convolve it against log of lambda minus lambda prime, then you get the delta function of
Thank you.
Okay, so now we're trying to okay, where was I? Sorry, I lost my. Okay, so that so usually we're trying to determine the coefficient of the double cone, and that coefficient is typically easy to do when we have a path integral, if we can interpret the path integral as a trace in some Hilbert space. So our first task now is to try to compute that. We're going to say that double cone wormhole can be viewed as a trace in a certain Hilbert space. So first, we'll try something that doesn't quite work, but a small modification will work. So if we are in the boundary theory, we know that we have this quantity is really a trace over the Hilbert space of the two boundary theories. And we can view it as, then we can view the wormhole as one particular state in the double theory. And then we could build a Hilbert space around that state. So in particular, whatever this whole trace is in the gravity will include a trace on the Hilbert space that is built on the two-sided wormhole. So we have the Lorentzian here, two-sided wormhole. There is a vacuum state, which is the Hartle-Hawkins state. And then we can act with operators. We can generate many other states. That gives us a Hilbert space. And then we can take the trace in that Hilbert space. So this is the trace in that bulk wormhole Hilbert space. That will be our first attempt. We'll try to compute this trace. Okay. these f's were these functions that were focusing us on some energy region. So h here will be the ADM energy on the left, h left, and h right is the ADM energy on the right. Now this is if you heard something about types of von Neumann algebras, this is a type 1 algebra, not type 2 or type 3 for the moment. Well, now we'll explain in more detail what the Hilbert space of the wormhole is. So first we'll focus on the empty wormhole with no matter inside. This is not one solution, but a family of solutions. And the family is parameterized by two parameters, two classical parameters. One is the mass of the two black holes, so we can increase or decrease that mass. And it's a continuous parameter. And the other is a certain relative time shift. This is a slightly more subtle parameter, so let me just try to explain it. So there are some times in the boundary theory, which we will call u left and u right. So these are the physical times that you measure on the two boundaries. And then there is some Schwarzschild coordinate t in the bulk. And so we could choose a gauge where the left time is equal to the Schwarzschild time on the left side, or let's say minus the Schwarzschild time if we think of the two times as going forward, the two boundary times going forward. Then here on the left we can choose it this way. But then on the right we have the freedom, we have the possibility of identifying u right with the Schwarzschild time up to some constant. And this constant then will be a physical parameter. It corresponds, roughly speaking, to shifting this wormhole up or down, or shifting the origin of time. And the presence of this constant is related to the fact that this wormhole breaks one combination of the time translation symmetries. So it preserves h left minus h right, but it breaks spontaneously h left plus h right. So it's a bit like the phase of a superconductor, or we could call it a time superfluid mode, that this wormhole is a kind of time superfluid in the sense that it's breaking time translation symmetry. And we have this degree of freedom. So we have a two-parameter family of solutions. And furthermore, if you can compute the Poisson bracket between these two parameters in the classical theory, and you get that the Poisson bracket is 1. So they are canonically conjugate variables in the classical theory. And for a very explicit discussion in the case of JT gravity, this was discussed by Harold and Jeffries. Now, so the full wormhole Hilbert space contains an L2 of R, so quantum mechanics of 1 degree of freedom, and its conjugate momentum. That is associated to this to the gravitational part, and then we have quantum fields in the fixed wormhole geometry. And if we have a higher dimensional theory, we'll include small fluctuations of the graviton, so fluctuations that do not change the mass, as within this quantum field theory discussion. So this operator K, which is a left minus defined to be h right minus h left, is a good operator in this part of the theory. And one can further say that h right minus this some reference mass m0, so that's this little m. So this little m is part of the black hole wormhole, empty wormhole degree of freedom. So these two are good operators. Okay, this is somewhat busy transparency, so let me try to explain what that is. So here we can say that we start from the microscopic theory. Then from gravity, we expect some contribution that comes from the wormhole, that is again a trace in that wormhole Hilbert space. And then we can just insert the previous expressions for the operator. So this is an operator in the quantum field theory part, and this is an operator in this gravitational part. And then we can rewrite this as some trace that is purely on the gravitational part of the degrees of freedom, and some trace which is purely in the quantum field theory degrees of freedom. And here we've assumed the Gaussian, so that simple splitting arises when we have a Gaussian window function. So we picked here a Gaussian window function, and we split the computation into two parts. One is the computation in the bulk quantum field theory, ignoring gravity, and this comes from these very simple gravitational degrees of freedom of the wormhole. And these traces are all well defined with a unit normalization, and unfortunately, we will see that none of these two operators has a well-defined, has a nice trace, and we'll discuss how to fix that. So we'll discuss these two factors in turn. So the first factor is something that involves the gravitational degree of freedom. So we could think of M as a momentum variable and T relative as, let's say, a position. And the problem is that then the trace of this function, of this expression, we can approximate it when h bar is small as an integral over the phase space, so dt dm divided by 2 pi. So this is good, well-defined normalization. Then whatever function we had here. So that was the Gaussian function, that was the square of the window function. And the integral over m is perfectly well-defined. So this function was normalizable, so that's perfectly well-defined. The problem is the integral over the relative time, and that will give us some kind of volume of the relative time, and that will be infinite. Now, on the other hand, so once we understand where this infinity comes from, we can say, well, from the picture of the wormhole that is compact, we see that it would be more natural to say from the, at least for this particular geometry, that the relative time is not really non-compact, but is actually compact. Okay, so that this relative time direction is t. In other words, if we view the computation not as a trace of that wormhole Hilbert space, but as some modified trace where we change the phase space, the phase space of this computation so that the relative time is compact. So if we say that the relative time is compact, that would be like a modification motivated by the geometry of this wormhole. And if we modify the phase space in this way, then we get precisely the right factor. Okay.
Can I ask a question, Juan? This calculation you did was the split you did between the M and the K, the QFT mode. This was a leading order in 1 over n split, I suppose.
Yes.
And, but this effect of the ramp is could be very sensitive to fine-grained corrections. In fact, the infinity that you're finding here is actually occurring, of course, because these different states at a large t relative are not exactly orthogonal, which eventually has to do with some fine-grained correction. So I'm a little, but I mean, is it justified to work at leading order 1 by n to compute this, to try and understand this effect?
Yeah. So I think you're raising the question of what the corrections to this computation are. So there could be further corrections from other geometries. So I certainly agree with you that there will be other corrections to this. In particular, there should be the corrections that lead to the plateau, just from answer analysis. Here, all we are trying to do is to compute the contribution from this particular geometry. I don't have we're not claiming that this is the full answer. We're just saying that this is here we're just trying to compute the normalization of a particular geometry, which is this double cone geometry. That was the objective.
I see.
I'm not sure if I've been clear.
Yeah, I'm not that. I mean, in particular, this fact that there's an infinity here is really occurring because we haven't been very careful about the inner product in the Hilbert space of the original work. Isn't that fair? Because you really assume that the e to the
yes.
So this
yes. Yeah, no, that's correct. And so the infinity here is reasonable, and in fact, this infinite contribution is actually related to the disconnected contribution to this computation that we are not discussing, the one that gives, let's say, e to the twice the black hole entropy, right? So there is a disconnected contribution that comes from two separate disks, and presumably this infinity is absorbed within that contribution.
Thank you.
So here, what we've done really is to first motivate the normalization of the path integral as if we were doing this other computation, but then we modified this phase space by going back to this wormhole picture and saying that the only difference between this previous computation and the computation in the actual wormhole is to compactify this time direction. we have not justified the compactification of this time direction from the point of view of this trace in the Hilbert space, but we justified it from the point of view of the gravity computation. And so, in other words, we are saying that if you do the path integral on this geometry, you will get a normalization for this path integral, which will be the same as if you were computing that trace, except for the compactification of the time direction. Okay, that's what we are saying. Now,
one question.
Yes.
Probably something that I didn't understand. I didn't quite get how this compactification leads to a finite domain for relative time, because I would have thought that has to do with the quantization of energy.
Yes, so this compactification leads to a finite range in time, and in addition, it would quantize this this integral over m. But we are thinking that h bar is very small, so we are ignoring the fact that this m is quantized. According to this argument, you would conclude that this m is quantized, but we are ignoring it, assuming that h bar is very small. So this
Hilbert space, high energy Hilbert space of quantum field theory, we don't expect any sort of uniform structure, right, in the spectrum.
No,
so
no. This should not be what? Yes.
Why is it that the trace would be periodic, some sort of a periodic function of t?
Well, I mean, here the periodic function of t is arising because of the computation that we are doing, right? It's similar to when we compute the thermal partition function, that we have something which is a periodic function of t, let's say in Euclidean time. Here we have a periodic function of t in Lorentzian time. And you can view that as a trace over some Hilbert space where the energies are not quantized, or there might be another way of thinking about it where all the energies are quantized and you do some other, computation. Similar to the question of in the Euclidean case, why we have only Matsubara frequencies while the ordinary Hamiltonian has arbitrary energies.
Great.
And sorry, Juan, you might be coming to this, but just to ask you, if you try to do the path integral on the double cone, it would presumably have some singularities because of this, the
yeah, absolutely. We are going to get into that in a second. Yes. So far we have this coefficient. So one conclusion of this discussion is that the double cone is not a trace in the Hilbert space of the two-sided Lorentzian wormhole, for which T relative is non-compact, but it is a trace in some other auxiliary Hilbert space where T relative has been compactified, and otherwise it's the same. So now we go to the second factor. So the one that in the quantum field theory roughly is trace of e to the minus I tk. Or if we include the window function, there is some extra correction, but doesn't make a big difference. So we're going to focus on this part now. And the coefficient of the ramp works as in random matrix theory if this is 1. And we'll get 1 here from the contribution of the Hartle-Hawking vacuum or the thermofield double. So that we just keep 1 here. So if the rest of the contributions are 0, we get the expected answer from the random matrix. But we'll see that we won't get exactly that answer, but it will be an answer that becomes that answer for very large t. But one first point is that this trace of this quantity can be viewed as compactifying the geometry by identifying two Schwarzschild times with each other. So this blue line with its other blue line. So this is the same as what we do when we have Euclidean time. So that's more or less natural. So that gives us, again, this geometry. Now, this second factor, as we were discussing, is not well defined either. And the problem is, the main problem is that the spectrum of K is continuous. It's not so much the large values of the energies, but it's just the fact that the spectrum is continuous. And from the bulk point of view, we have that shrinking time direction at the horizon. So that those are the reasons why it's not well defined. Now, Saad, Shenker, and Stanford proposed to modify the definition of K by a certain I epsilon prescription. And this amounts to basically modifying the geometry of the wormhole. So the original geometry of the wormhole the original geometry is just the usual geometry of a Schwarzschild black hole, where let's say rho is the distance from the horizon. And f becomes 0 at rho equal to 0, that rho equal to 0 is the position of the horizon. So the idea is that the true geometry that describes this process is one where we consider a coordinate rho, which is rho tilde minus I epsilon with real rho tilde. So another way of thinking about this is that in the complex rho plane, we were initially thinking about geometry that runs along the real rho axis, but now we consider one that where rho is slightly deformed into the lower half plane. So we're going to define, so that they define really modified boost to be the generator of T translation in this new geometry. And we're going to call that K tilde, okay? So again, this is so the idea is that the true geometry is the one with this I epsilon prescription. So now the circle does not shrink to 0, and the path integral is well defined. In fact, it obeys this Kontsevich-Siegel criterion for a well-defined path integral. Was there a question?
Is this the same as adding a little bit of Euclidean time evolution?
No, it's not.
Okay.
So the other epsilon prescription doesn't work, and this works. The other side.
Well, this is the I epsilon prescription that works. I'm not sure which other prescription you have in mind.
Well, the one that goes above it.
Plus I epsilon.
Sorry.
Yeah, plus I epsilon.
Sorry, could you say it again? I didn't hear.
No, I just mean I don't quite see how this I epsilon prescription is motivated. That's why I'm asking if the minus sign were plus, would that not work?
Okay. Yeah, so yeah, if the minus sign was plus, it would not work. Let's say that this I epsilon prescription was motivated by, so that they motivated it by first starting with some simpler quantum mechanical models, like Brownian SYK and then SYK. And then when they went to gravity, they found that this gives the right prescription. So indeed, I feel I don't have a very deep understanding of how to derive this prescription, or even what this prescription means. And part of why we were looking at this was to understand better this prescription and its meaning in the full theory. Here we're just going to say, well, we take this prescription as given as a definition of what the geometry we are considering is. Okay. And we see that the circle doesn't shrink if we take the minus I epsilon. Now the sign, that sign, you asked me about the sign. So if you take it with a minus sign, you find that the path integral, it's a bit more like a Euclidean path integral where you suppress the large fluctuations. And if you were to take the other sign, you will get something similar to Euclidean path integral with the wrong sign, the wrong overall sign. Okay. Like Euclidean path integral over negative Euclidean time rather than positive Euclidean time. So that's something that is easy to see that one works and the other one doesn't. So now we'd like to understand the properties of this new evolution on these geometries. So this small I epsilon deformation drastically changes the spectrum. And the spectrum of K is continuous. And it's a Hermitian, K is a Hermitian operator, has a real spectrum and with continuous eigenvalues. And this, once you make this deformation, you find that discrete k tilde has a discrete spectrum with complex eigenvalues. So k tilde is not a Hermitian operator, and it will have complex eigenvalues. And the spectrum of k tilde, so there is a typo here, this should be k tilde. So the spectrum of k tilde is actually equal to the spectrum of quasi-normal modes on this black hole. So I'd like to explain this a little bit. So the next transparency is kind of explaining where this comes from. It just comes from basically doing the calculation that you find that the equations that determine the spectrum are the same as the equations that determine the quasi-normal modes. I'm not sure if you should have expected this from the beginning, but this is what turns out to happen. So, this we understood that by considering the scalar field on the black hole background. So you write down the wave equation. So this is just a calculation. So, so you get the second order equation for the function of rho. You can also do Kaluza-Klein expansion in any other extra dimensions that you have. And then, so when you solve this equation near the horizon, you have two pieces, one going like rho to the I omega, one going to rho to the minus I omega, with some coefficients A and B. And that's what you get for rho bigger than 0. For rho less than 0, you get exactly the same expression if you substitute rho to minus rho. And now, if you demand that that these two functions, well, first of all, so if you demand that these two functions are continuous as you move in rho from one side to the other through the lower half plane, then it leads to some conditions on these coefficients. So one way to obey it would be to say that omega is equal to in, for example. Then this would be an integer and it will continue fine. And if not, then it will impose these conditions once we also take into account that there is a Dirichlet boundary condition at the boundaries, at the boundary of ADS, for example. And so these conditions that A or B are 0 are the conditions that give the quasi-normal modes. They are saying that the quasi-normal modes are the smooth in the future horizon, and B equal to 0 gives the anti-quasi-normal modes, so smooth in the past horizon. And we pick the quasi-normal modes because they have the right sign for the imaginary part. And these ones, in general, do not lead to good solutions. So quasi-normal modes, of course, are basic properties of black holes. We see them in the LIGO waveforms, for example. And they reflect longer-lived modes that thermalize more slowly. So the final result is that this part of the trace of K tilde is the product of all the quasi-normal modes, and each quasi-normal mode gives some factor that looks a bit like a harmonic bosonic harmonic oscillator or a fermionic harmonic oscillator in this expression. And this whole factor multiplies the expected ramp factor. So if t goes to infinity, if all these things have a positive, a negative imaginary part, then they will all go to 1. This whole factor goes to 1. But generically, it typically is larger than 1 if this, let's say, have a purely imaginary part, so that they are purely decaying, then this factor will be typically bigger than 1. And that implies that we don't have chaos within the full system, but we have chaos within separate subsectors. So somehow there are quasi-conserved quantities associated to these quasi-normal modes, and then the system is chaotic within each subsector. So before I was asked whether we really get the random matrix behavior, and here we see that from gravity we do not get the random matrix behavior. We get some correction that is due to the quasi-normal modes. It's a correction that disappears when we go to very large times, but is present for finite times. And it's representing this lack of full thermalization or chaotic spread, or the spread of chaos within the full system. Now, in particular, there are some quasi-normal modes that come from hydrodynamics in cases where the black hole has some hydrodynamic degrees of freedom. And in this case, this formula that we just discussed matches the expressions that were obtained for the spectral form factor from hydrodynamics. So Swingle and Wiener computed the spectral form factor in cases where we have a hydrodynamic description, and there is a particular expression for this quantity that we can derive from the quasi-normal modes, and it agrees with what they had. Now, we were surprised by this drastic change in the spectrum due to the I epsilon prescription, and we wanted to understand a little bit better where that was coming from. So in case you are also surprised, we'll discuss a simple toy model where something similar happens. Now, first, before we discuss the toy model, we'll recall.
Can I ask a question?
Yes.
Hi, Juan. Yeah. So usually quasi-normal modes arise when you have a black hole at equilibrium and you throw some stuff inside, and the system sort of oscillates to equilibrium again. So where is that physics actually in this analytic continuation of the metric?
Yes. So here we're not throwing anything inside.
I know,
but the quasi-normal mode is a kind of normal mode oscillation of the system. And here in this expression, what is happening is that the quasi-normal modes are somehow going around the time loop, essentially. So we have a closed time loop, and the quasi-normal modes are propagating there and giving rise to this contribution. That's roughly the idea. So in the same way that if we had a system with a compact Euclidean time direction, we would have ordinary particles or ordinary, let's say, physical degrees of freedom going around the time circle. The Euclidean time circle will give rise to an expression similar to this. Here, the only difference is that these frequencies have some imaginary parts.
Okay, thanks.
Yeah, in particular, this something I found, well, we find interesting is that by thinking about this operator K tilde, we view the quasi-normal modes as the eigenvalues of some non-Hermitian operator, of a very specific non-Hermitian operator is well defined in the full quantum theory. Okay, so we're now trying to discuss this this change in the spectrum, and first we'll discuss what happens in the ADS2 discussion. So for black holes whose near horizon geometry is ADS2. So in that case, we actually have an SL2. We have SL2 symmetry generator. So K is one of them, but we also have something that we can call H and P. So they have one is roughly like time translations, and the other is roughly like space translations. They don't obey quite the Poincare algebra, they obey the SL2 algebra. So this is something that we have in SL2, but not in the Poincare algebra, but we're using this Poincare notation because that's how the generators act near the horizon. So in this case, the modified boost can be obtained by changing rho to rho tilde minus I epsilon. This is a kind of translation by an imaginary amount. So we can think of K tilde as resulting from a conjugation by a translation by a finite amount. And that's, so we get this particular linear combination of operators with an I here. So it's a non-Hermitian operator. H is the Hamiltonian of in global ADS2, so it's a positive operator, or well, I should more precisely say it's a non-negative operator. And so K tilde has a negative imaginary part, or well, it could also be zero. Okay, now writing it as a conjugation has a certain advantage, which is that the spectrum is at least formally independent of this alpha, or the alpha is roughly like the epsilon we are using to make the deformation. And that's because if, let's say, K tilde has a certain eigenvalue for a particular lambda, and then we conjugate by a U, so U would be this e to the alpha p, which is not necessarily unitary, then U times lambda will be an eigenvector with the same eigenvalue. Okay. So the eigenvectors and the eigenvalues are the same for U and this conjugated version. And in particular, if in the previous expression we set alpha equal to pi over 2, then this term vanishes and this term becomes 1. And so that implies that the spectrum of K tilde is the same as the spectrum of the global time Hamiltonian, and that's discrete, so that's IN. So, and this is indeed the spectrum as long as alpha is different from 0, but not for alpha equal to 0. So for alpha equal to 0 is when we had the continuous spectrum. And in order to understand what's happening and why there is that difference, we can even go to an even simpler model where we have just the standard single particle Hilbert space on a line. You can think of that as the Hilbert space of a harmonic oscillator, where we have operators A and A dagger, and then we can realize H to be more or less the standard Hamiltonian harmonic oscillator, and K and P to be these other operators. And with this definition, K is something that roughly is like a rescaling of X. And then we see that we have eigenfunctions with continuous eigenvalue omega, which are of this form, just X to some power. Okay, and the spectrum is continuous on the whole real line. But now we can again do these similarity transformations, and what happens is that what will happen is that for when we go to alpha equal to 0, this eigenstate, the new eigenvector, might not be normalizable. So it takes it out of the Hilbert space. And one can see this very explicitly in this toy model, where for finite alpha, the eigen functions are just Gaussian, but the width of the Gaussian is going to infinity as alpha goes to 0. So that's the mechanism by which the spectrum changes drastically. Okay. So at alpha equal to 0, all these states that were non-normalizable become normalizable. Okay. So in conclusion, we see how a small deformation can drastically change the spectrum in a way that is somehow independent of the deformation. So once epsilon is non-zero, we have a new spectrum that is independent of epsilon, but when epsilon is 0, we have a different spectrum. Okay, so let me see, how am I doing with time? Okay, so so in ADS2, we have this kind of structure, and one can generalize that structure for the general black hole case. So what follows is a somewhat formal argument that is based on some recent algebraic discussion of the modified boost and the quasi-normal modes for general black holes. So what we are going to do now is try to make the discussion for a general black hole look somewhat similar to both the toy model that we discussed and the ADS2 case. And for that, we'll define 3 generators which annihilate the vacuum, which will obey this type of algebra. So we had the operator K, so we're going to define new operators H and P that will obey these 2 commutation relations, though this one will not be obeyed, so it will not be SL2. So we already defined K, and if we were in flat space, we could easily define the other 2. They were just the symmetries of flat space. And the idea is that in the black hole background, we can use the so-called modular inclusions to define 2 operators which have similar properties to P plus and P minus in flat space. So this is done by considering, this is something that can be done whenever we have wedges, whether we have these wedges in flat space or let's say in the black hole case. And so we can consider a subwedge, so a subregion, like for example, this subregion here. And we can consider the modular Hamiltonian of this full region or the modular Hamiltonian of the smaller region, of the R plus region. And we can consider the difference between the 2 modular Hamiltonians. And in that way, we can define some operator, which we're going to call P hat minus. And this is just the definition. And we can do the same thing here with the other object. And it turns out that these operators, one can argue that they are both positive semi-definite and that they obey these commutation relations. So they look a bit similar to P plus and P minus, but they are not exactly the same because there is no commutation relation between this guy and that guy. But then we can define formally these operators. This type of construction, well, it's some older construction, but it was recently discussed in this context by Liu and Leuthausen. But now we can define the operator K tilde as a conjugate. This is formally. I say formally because these operators are very hard to construct explicitly. I mean, for free fields, you can. They were constructed fairly explicitly by Liu and Leuthausen. But then we can take this K tilde and define it to be the result of this conjugation by a small epsilon. And if we define it this way, then we see two things. One is that by using the algebra, we see that this operator was positive semi-definite. And so that shows that K tilde has a negative imaginary part. And also the fact that we can write it as a conjugation, the eigenvalues are independent of epsilon for positive epsilon. So this gives a somewhat algebraic description of the quasi-normal mode problem. Okay. And well, in addition, we expect that near the origin, these operators are like translations. And indeed, the change in rho to rho plus I epsilon can be locally understood as a result of a translation by an imaginary amount. So we expect that this algebraic definition should agree with the Saad Shenker Stanford definition and lead to the same spectrum. Okay. Let me see. Okay, so I'm slightly over time. So this whole discussion was purely in the bulk theory, and the question is.
You don't have to worry about time. Please go ahead. Go on as long as you like.
So I think, I mean, our goal was to understand better geometrical aspects of these black holes, and then perhaps understand better what, perhaps learn some lessons about why these black holes are given a non-factorizing answer and things like that. Now, we were not successful in the second part of the questions, so I'll now try to go into this discussion. So far we discussed a few results, and what I'm going to discuss now are mainly some questions, or let's say, well, natural questions you can ask. So the first, some points. So in the bulk theory, these operators we define, H hat, P hat, and so on, are operators that act on both sides. So they are not the sum of an operator that acts on different sides, such as K. So K is like H left minus H right in the macroscopic theory. So H hat and P hat are operators which really are acting on both sides. Now, in the bulk theory, we can define the factorization of the type 1 algebra of the wormhole into two type 2 infinity algebras, A left and A right. And these generators H hat and P hat do not act as automorphisms within each subfactor, in contrast with what happens with K. Now, this would suggest that the I epsilon deformation, which involved adding these operators H hat or P hat, is introducing a coupling between the two sides. So this is just some indication, at least if you do this construction. Now, also in the ADS2 case, they also had a similar conjugation by a momentum generator, and this momentum generator, if we view it as the physical momentum generator of JT gravity plus matter, again, we have an operator that acts on both sides. So the gravity discussion was based on constructing the state by operators that acted on the thermofield double in the Larsen limit. And in the Larsen limit, we don't really have something that factorizes in the boundary theory. So in some sense, the whole construction of the thermofield double Hilbert space is not something that clearly factorizes in the boundary theory into two factors. So somehow if we if we use a construction that is only valid in the Larsen limit, then we cannot ask this question about factorization in the macroscopic theory.
Sorry, Juan, can I just ask you there? Is that because the Hamiltonians are the same on both sides? Is that what you mean by no factorization in large N, or what did you mean?
It's mainly, let me explain what it is in more detail here. So the Larsen algebra of the wormhole does factorize into two type 2 infinity algebras, as Edward discussed recently. Witten discussed recently. But the computation of the trace in the full Hilbert space does not factorize into two separate traces. In other words, so if we could calculate, so there is this type 1 trace that is defined in the full Hilbert space, and these two operators factorize into two separate operators in the type 2 infinity algebras. And the type 2 infinity algebras involve some definition of trace, but that definition of trace is not equal to the, so this type 1 trace is not equal to these two type 2 traces. So that's not true. Because in defining this type 2 trace, we are subtracting some infinite constant. So this thing here in the right-hand side is somewhat like the disconnected contribution to the spectral form factor. So it will give us the disconnected contribution up to an overall constant. That is the constant that is subtracted in defining that type 2 trace. I'm not explaining too much of the details of this. Well, this discussion might not be very clear if, here this type 2 trace is the trace that was defined in the recent papers by Ed Witten on this topic. So this type 2 trace is basically the trace on a one-sided Hilbert space with some infinite constants subtracted, which is the classical black hole entropy, the area term. But it can be defined completely formally in an algebraic sense. So we wanted, so that there is here one philosophical comment that is related to a question that was asked in the beginning of the talk. So I epsilon prescriptions such as Feynman's prescription, for example, I epsilon prescription, are not mere mathematical tricks. They usually imply some physical choices, like, for example, the choice of vacuum in the Feynman case. And I don't feel I have well, we haven't managed to have an understanding of this I epsilon prescription that Saad, Shenker, and Stanford did that is, as precise as the one we have for the Feynman one. So for now, it's just the prescription, and its full physical implications we have not understood. So, that's part of that's one thing that one would like to understand better. So whether this prescription implies is or is, so one question we were trying to understand, and whose answer I don't know, is that whether this I epsilon prescription is what so one conjecture one can have is the following, that the I epsilon prescription is responsible for having a non-factorized answer between the left and right side. So one could conjecture this, and what I discussed, the points I've just made are in favor of this interpretation. But now I make some points which are against this interpretation. So, in fact, perhaps there is another way of thinking about it, which does not involve the coupling between the two sides, and we'll see that happens in some cases. So, let me just jump over. Well, well, how much detail do you want me to give on this? Okay, I'll continue speaking. Maybe. I was given free range in terms of time, so I'll do that. So we'll discuss now the computation this type of computation of spectral form factor in the case of ADS2 and JT gravity case, where it's particularly simple. And in that case, there is an interesting thing one can do, which is one can take into account the gravitational back reaction and see what happens in that case. And so the idea is that we like to understand how the fields in the bulk CFT affect this double cone geometry. And what one finds is that the presence of these quantum fields, so these are the same fields that were giving rise to the quasi-normal modes, but now we take into account the fact that because we have those quasi-normal modes going, they deform a bit the gravitational part of the computation. And what they do is they do an I epsilon deformation, but with the wrong sign. So if instead of, so they give a geometry that is deformed with a complex deformation, but with the wrong sign. And something similar was found in a somewhat related computation by Kotler and Jensen, where they were putting complex couplings. Now the question is what we should conclude from this. It looks naively like an inconsistency in the sense that we consider the quantum fields, assuming that the path integral over the quantum fields is well defined, but then we got that the deformation was in the wrong direction. Now,
sorry, I didn't understand. When you said it deformed it in the wrong way, you meant one computes, say, the back reaction due to the quantum stress tensor, or what did you mean?
Yes, indeed. That's the computation. So we take the double cone, we compute the quantum stress tensor, that gives rise to non-zero value of the stress tensor, and that deforms the geometry. And the deformed geometry is the same as the original geometry plus I epsilon instead of minus I epsilon. But where epsilon is something finite, so it's this rho star that we're discussing here.
Okay, thank you so much.
That's what you find, and what we're trying to discuss is what the interpretation of that is. So one way to think about it is that, well, what we really need to do is deform the integration contour so that it does not go along the red line, but it continues to go somehow below the original zero that we had here. Okay, and this green contour actually gives the expected answer. So it gives that gives an answer that is reasonable from the boundary theory point of view. So naively, one might think that this looks like an inconsistency, but I think perhaps the most conservative option is the following to interpret this result. It is that we consider first an off-shell geometry with the good sign. We do the path integral over the matter fields with this off-shell geometry with the correct sign, where we can do the path integral according, the path integral is well defined. And then after we get the answer for the path integral, we analytically continue in the deformation parameter when we do the final integral for the gravitational degrees of freedom, which, let's say, for example, these Schwarzschild modes. And this gives the answer we expect. So this is, I think, the most conservative interpretation of this answer. Okay, so now finally, I'd like to discuss a situation where we get the deformation with the right sign by modifying the computation that we're doing. And
can I ask you one more question about that, including the matter, if I may?
yes.
If you do just the double trumpet computation in JT gravity matter, as you know, there's a Casimir divergence you get. Is there anything like that here? It seems like it's well defined, just gives the opposite sign for the I epsilon.
Yeah, so the double trumpet in just JT gravity with no matter is well defined, so it gives a correct answer. I think what you mean is JT gravity plus matter, right?
Correct.
And yeah,
yes.
that's what we are talking about here. So we are talking about here doing the JT gravity plus matter computation. And we are discussing the saddle point solution, which corresponds to this particular finite value of epsilon. As you correctly say, if we go off shell and we consider very thin, a very thin trumpet, then we say divergence. So the full computation diverges, as you correctly say. We're interpreting here that perhaps this divergence is absorbed in the two disconnected, in the answer for the two disconnected pieces, the two disks. And we are really focusing here only on the saddle point contribution.
Okay,
So,
I see. I understand. Okay, I
so
see. Where
we're
road
taking
this?
we're taking a very conservative point of view here of just computing saddle points, but saddle points including the quantum corrections.
Okay, okay, I understand. Thank you.
We're only including the quantum corrections perturbatively. Yeah.
Right. Okay. Thank you.
Yeah.
Okay.
So before we were saying that because we were saying that perhaps the I epsilon deformation introduces a coupling between the two sides. Now we're going to argue for the opposite. So we're going to consider a situation where
give us a minute because suddenly the projector screen went off. We can still hear your voice, but the minute we will fix that.
Okay.
Just see the light.
Yeah, the light is coming.
So what's the reason why?
Oh, it starts feeding. It starts feeding.
Yeah.
You can switch it off.
Yeah, switch the projector off and on again.
Yes. Is there a loose connection?
That's not sure.
Suddenly.
What did you say?
That's what I think. There is loose connection somehow.
Oh no.
It starts feeding it down.
Is the monitor movable? What is this?
Yeah. On.
You think it's the computer?
No.
That's showing one
Yeah,
profile.
computer is fine. Where is the what is the host signal status for activities? Should I call it up?
Yeah. So maybe the monitor can be brought out to the podium.
This one? Yeah, we can try to pull
See
this
if that
up.
can be more.
Yeah. Okay. Yeah. Let's continue. Yeah.
Is that better?
Yeah.
Okay. Okay, so we have managed to pull the monitor so that everyone can see it. So please do continue on. Sorry for the
Okay,
break.
great. So thank you. So we'll now discuss a situation where in the macroscopic theory, the computation is really factorized between the left and the right system, but nevertheless, we have an I epsilon deformation with the right sign. And the idea is simply to take the same setup, but we add imaginary boundary conditions for a back scalar field that is opposite on the two sides, or add imaginary couplings, so let's say fixed imaginary couplings similar to, and this gives a contribution which has the right I epsilon prescription. And here the boundary theory completely factorizes, and in this case we expect that this operator K tilde, which would be the quantity that factorizes in the boundary theory. So where H, here it should say H tilde left and right, would be H and plus or minus some imaginary coupling. So O is a Hermitian operator. In this case, there's a computation very similar. Well, essentially the computation that was done in this paper shows that this quantity factorizes. Okay, so now one final comment. This is So, well, I don't have anything to say about this. This is, I think, a well-known thing. But so whenever you have one of this type of space-time wormholes or Euclidean type wormholes, then you can cut the wormhole at this moment and then continue it to Lorentzian time, and you get some kind of closed cosmology. So in the case of the black hole, if you continue the analytic continuation that continues along here, the imaginary axis, then what you get is the interior geometry of the black hole. So this analytic continuation we were discussing is somewhat related to the continuation that gets us into this vision. I don't have anything more to say about this. I'm just saying it just for general culture and to remind you of this. So a deeper understanding of this wormhole hopefully might also help us understand the black hole interior. That's all I'm saying. But I don't have anything more to say about this. So in conclusions, we've discussed some aspects of the double cone wormhole. One point was to describe it as a trace in the bulk Hilbert space, which gives us the right normalization after we compactify the relative time shift coordinates. So that was one point. The second point was to show that the eigenvalues of the modified boost are given by the quasi-normal modes. And then we gave a general algebraic definition of this modified boost operator. And then we had some discussion about whether the I epsilon prescription induces or does not induce a coupling between the two sides. And we had some arguments for and some arguments against that point of view. And so this part of the discussion was inconclusive, hopefully might be understood in the future, or perhaps this question of whether there is a coupling between the left and the right cannot be decided purely by looking at this geometry, but might involve the full sum over geometries, on exactly how we treat the full sum over geometries. Okay, thank you.
It's okay with you, Juan? Maybe we can have some more questions.
Sure, yeah, go ahead.
I have one question. Can I, Abhijit, can I ask a question?
Yes, well done.
Yeah. So, so if we consider a scalar field in the modified geometry, what is the boundary condition at the horizon?
The boundary condition is that the field should be continuous as we go from the left, right to the right side by going through the lower half plane. Let me be more precise. So, we have find the right picture. So here we had this discussion. So the field should be continuous along the blue curve. So that's the boundary condition.
I see.
So we're not imposing the field vanishes or anything. We're just saying that we should join the left field with the right field in such a way that they are smooth here.
So it so happens that the spectrum that you get this way seems to be similar to working with the old geometry with the wave operator with infalling boundary conditions, right?
Yeah, that's what it turns out at the end.
I just wanted to understand what is the connection which I asked before also, actually.
Yeah, so why that is the case, I think required some calculation and some discussion. But yeah, maybe there is a quicker argument that doesn't go through the more explicit calculation we did here. It certainly would be nicer to find a quicker argument.
Thank you.
Reason why that should be the case. This type of analytic continuation, somewhat similar to this, is similar to what we do when we select, for example, the Minkowski vacuum when we talk about the Rindler wave functions. It's somewhat in that spirit, but it's slightly different in detail in how we treat the positive and negative frequency modes. But at least for half of the modes, it's more or less the same.
Sorry, Juan.
Let me be more precise. So let me be a little more precise about that comment. So when we talk about the usual discussion of Rindler modes versus Minkowski modes, we do a similar analytic continuation, but the analytic continuation in that case is in the time variable. So we analytically continue the time variable as opposed to the raw variable. So that's the difference between the two cases.
Thanks for a very stimulating talk.
Sorry, Juan. If I can go back to the start of your talk, you mentioned that one way in which perhaps we could understand the lack of factorization is if we are doing a time average, which sort of might reproduce an ensemble average. And here you seem to be finding, if I understand your interpretation, that what you're finding is that the I epsilon prescription actually just induces an explicit coupling between the two sides. So it's not so much related to a time average as such. Or is there an interpretation like that which is possible?
Well, I don't want to commit too much to that interpretation, but that's interpretation that is suggested by this discussion of the modified boost operator and how that's only an interpretation that is suggested by, let's say, these formulas that we're discussing here. Let's see, where was the by this type of formulas, right?
Right.
Now, the thing is that maybe there might be some other way of defining K tilde which does not involve the coupling between the two sides. So we did not show that there was not another way of defining it. So suddenly with this definition, you need a coupling between the two sides, but there might be another definition that does not need the coupling between the two sides. So if you want, and also we discussed around here that there is a different context in which this deformed double cone geometry arises, which is a context in which the microscopic theory is really decoupled, but it has imaginary couplings.
I guess this. So the microscopic theory is decoupled in this case? But
yeah, so in this case, the microscopic theory is decoupled. It is completely decoupled. It consists of traces of e to the I, let's say t h left, and a trace e to the I minus I t h right, where h left and h right are given by this expression. So this setup connects a bit the double cone wormhole with ordinary Euclidean wormholes. So the ordinary Euclidean wormholes, let's say, for example, the axion wormholes, also involve imaginary values of the axion field, right? So they are somewhat similar to what we are discussing here, where we have some imaginary values on the two sides, which are different. They are opposite.
Sorry. Yeah. No, I didn't. But if they factorize, then why do you have a non-trivial connected two-point correlator for Z? Even if it is
yeah, well, that's somehow the puzzle, right? So so there is a well, I think the current interpretation for why we have that is that we are somehow doing an average over couplings. This is the current understanding of this. That in the theory, somehow we're averaging over some couplings.
I see. Not that it's a time average. I mean, couldn't it be? I mean, I don't know. Isn't the time average a more conservative interpretation?
Well, that could also be, yeah. So maybe we are doing that time averaging, an average over something in a connected way somehow. That we
Okay. Thank you so much.
Yeah, sure.
Right. One, two things your formulas reminded me of in some sort of vague free association with. First, there was this formula by Denef, Hartnoll, and Sachdev computing the determinant around black holes as a product over quasi-normal modes. I was wondering whether there was any relationship between that and your product over quasinormal. So the second question, as vague, is
yes. That's a very good question, and indeed there is a relationship. Let me go back. Well, let's see. So they had a formula expressing the answer in terms of products of quasi-normal modes, right? And if you take their formula has some explicit betas, so it has beta times the quasi-normal mode, and the quasi-normal mode itself depends on the mass of the black hole, right?
Yes.
If you somehow fix the mass of the black hole, and you analytically continue the beta that appears multiplying the frequency to IT, right? And you take the product of their formula and their complex conjugate, right? Or their formula and the formula with minus IT, you take the product of those two things, then you get our formula.
Okay.
Let me just first say something simple. Yes, there is a connection between their formula and our formula. I was just trying to explain what the connection is. So there is a mathematical identity that relates their formula to our formula.
And is there a logical connection between these two formulas?
There should be, yes. Well, we haven't derived it completely. The first thing is to realize that well, here I'm speculating a little bit, but I think their formula can be derived from, well, let me just say that probably there is, but I don't know all the details.
Sorry, one more.
But let me just mention one point, which is that their formula is that those type of formulas are closely related to the idea of viewing the one loop determinant as arising from some kind of scattering problem from the past horizon to the future horizon. And it's related to some formulas that I think Albert Law and collaborators recently wrote down. So a formula where you view the one loop determinant in terms of the scattering problem.
Sorry, another big free association question. The contour you were writing down was reminding me a little bit about the contours that Hong Liu and Loganayagam and others have been looking at when looking at Schwinger-Keldysh correlators.
Yes.
Again, they have two copies of the bulk, and they're connected by going round in row. And I was wondering whether there was some connection.
Yeah, again, they look fairly similar. They're usually expressed in terms of the retarded time, so slightly different. But yeah, it would be nice to understand the connection more precisely. We did try, but we found somewhat similar, but not identical.
Thank you.
Okay, if there are no further questions, let's thank Juan again for our wonderful talk.